I mentioned in our first video that we have different ways of representing a graph in a computer, which is what we are sort of more interested in. We have a simple graph here, which I've drawn for us, have pre-rendered for us. I did not draw that. My handwriting is not that good. And we're going to write down what are the set of vertices and the set of edges and talk about why maybe those aren't the ideal way to represent this graph. So we're going to write down what V and E are in their entirety, unlike we did before, which is sort of why we punted on that earlier. The set of vertices is V1, V2, V3, V4, and V5. The set of edges is, we'll start with V1 because that's the first numerically. V1 connects to V2 and V1 connects to V3. We also have V2, which connects to V1, but we've already covered that. And it connects to V3, V4, and V5. So we need to write all of those down. So V3, V4, and V5. And then we have V3, which connects to V1, already covered that. V2 already covered that. V5 is new. We then have V4, which connects only to V2, and V5, which connects to V2 and V3. That's already covered in both instances. So we are actually done with our set of edges there. You may have learned about in the past how to program a set. The problem is that that's not typically what we need to access. There are two common things that we need to figure out when we are dealing with graphs. Often, the questions you want to ask are you're going to look for all vertices that are adjacent. So the question we had before of, for example, which airports are reachable in one flight from Columbus? Where are there direct flights from Columbus? That is a relevant question that we might want to ask, and that's not necessarily obvious of how we would look that up in a set, because it's not necessarily clear how you would access that. Granted, V1, V2, V3, V4, and V5 don't have meaning, but that's not necessarily an obvious question. The other question we want to ask often is there a flight between these, or is there an edge between these? So I want to know, hey, is there a flight that goes from Columbus to San Francisco? And I want to be able to look that up quickly. So with those two questions in mind, how can we represent this? Maybe we can't come up with this on our own. There are two main ways of doing this. They're called the Adjacency List and the Adjacency Matrix. So we're going to do Adjacency List first. Adjacency List. In programming, this is often what you will use because it turns out that that application I mentioned of what vertices are adjacent is much more common when coding than when analyzing these things mathematically. So what is an adjacency list? For each vertex, we are going to store the vertices that are adjacent. So we have V1, V2, V3, and V4, and V5. And for each of those, we're going to say which vertices are directly touching it. So for V1, we would keep track of V2 and V3. V2 is touching 1, 3, 4, and 5, so we're going to keep track of all of those. V1, V3, V4, and V5. And you'll notice something I've done here, which is I've actually stored that V1, V2 edge twice. Because I have in V1's adjacency list, V2, so we have V1, V2, and we also have V2, V1 that is already directly stored within the adjacency list. This is common where you'll double count the edges because they don't have a directionality and the user doesn't know ahead of time which one you're going to access first. You might be starting at LaGuardia, you might be starting at Columbus. We'd want to be able to access both directions if there's a flight between those two. For V3 is adjacent to V1, V2, and V5. V4 is adjacent to only V2, and V5 is adjacent to V2 and V3. So this is the adjacency list. This is one of our representations. This is useful because if I want to know what's adjacent to V1, I can immediately look up V1 and then access everything in that list. In practice, that V1, V2, V3, V4, V5 is stored in an array, which means you have instantaneous random access lookup. I can go access any vertex, numerically at least, instantaneously and then find the vertices that are adjacent to it. So I could go to the fourth entry in my array instantaneously and then process through a list. The list is typically stored as a linked list, often a doubly linked list, but singly linked list works well for most applications as well. And that is our first representation. Again, in coding, this is often what you do. However, this is not a useful thing to work with mathematically, it turns out. The way that this is frequently better mathematically is what's called an adjacency matrix. So off to the right here, we're going to have an adjacency matrix. Adjacency matrix. What we do here is we create a matrix of size, the number of vertices by the number of vertices. So I'm going to create a matrix. You may have never seen a matrix before. We'll talk a bit about them, but not much. A matrix is a way that you can store sort of lots of numbers in a 2x2 grid. They represent a bunch of different things. In practice, they probably are introduced most commonly as a system of equations, but they can represent a whole bunch of different things, and they're useful in equally as many applications as would show up in graphs. In fact, one could argue a course in linear algebra might be the most important course in mathematics that you take as an undergraduate in any engineering field, actually. What we do here is we're going to sort of label this matrix by having 5 columns and having 5 rows. 1, 2, 3, 4, 5. I apologize for my terrible choice of colors there. And we're going to represent if 2 vertices are adjacent by lining up their row and column. So one of these set of rows will correspond to V1, one of the rows will be V2, one of the rows will be V3, one of the rows will be V4, one of the rows will be V5. One of the columns will be V1, one of the columns will be V2, one of the columns will be V3, one of the columns will be V4, one of the columns will be V5. So if there is an edge between them, we're going to put a 1 in the matrix, and if there is not an edge between them, we will put a 0 within the matrix. So there is an edge between V1 and V2 and V1 and V3. So in the V1, V2 row, we're going to put a 1, and in the V1, V3 row, we're going to put a 1. Similarly, in the V1, V2 column, we will put a 1, and a V1, V3 column, we'll put a 1. We're going to come back to that, actually. We're going to hold off on that, and we'll see that this happens automatically. We're going to do the rows first, and everything else will work out automatically, it turns out. So we're going to undo that. And we're going to put zeros in every other location because there are no edges there. Then we look at V2. V2 is touching every other vertex. So there's going to be a 1 in the V1. There's going to be a 0 in the V2, and then a 1 in every other location. V3 is touching 1, 2, and 5. So in 1, 2, and 5, there's 1s, and then everywhere else there is 0s. And then in V4 is touching only V2. So V4, V2 has an entry, and that's it. And then there's 0s otherwise. V5 has 2 vertices that are adjacent. There is V2 and V3, and otherwise no connections. And if you look at this for long enough, you might actually notice that this is symmetric across the diagonal. That will always happen in an undirected graph, it turns out. The nice thing about the adjacency matrix is I can instantaneously look up if an edge exists. If I want to know, is there an edge that connects V2 to V3, I can access 2, 3 and check. I can go to 2 and then over to 3 and check, is that there? And both of those are instantaneous. If I wanted to know in the adjacency list, you might have to process that entire list. In the worst case, that could take quite a while. So adjacency matrices are better at looking up does an edge exist, and better for mathematical operations, where the adjacency list is often better for processing nearby vertices, which is why the adjacency matrix is often better mathematically, because you can write down properties of that matrix. There's the entire field of linear algebra to draw upon for analyzing matrices. And the adjacency list is often better for computer science because we're often what we call traversing the graph. We will deal with actually graph traversal algorithms later in this class, which are depth first search and breadth first search. We'll deal with both of those later in this class, and we will use the adjacency list representation for those algorithms. So this is the adjacency matrix and the adjacency list. They store the same information, but in different amounts. We can figure something out, actually, which is how much memory does this take? The first one, the adjacency list, we're going to have to come back to that. It turns out we don't have the information to deal with that. The adjacency matrix is easy, though. We have a matrix that is the number of vertices by the number of vertices. That takes the number of vertices squared storage, which is one downside to it. It turns out that in practice, the number of vertices is catastrophically big. The number of vertices can be on the order of billions to trillions. As an example, a company like Facebook has billions of users. I don't know the exact number, at least over a billion. And if you want to visualize what is the connection between every single person, that's a billion vertices. And God knows how many edges. Storing a billion square entries is not ideal when, in practice, you probably only know a small number of people. So if storage is a concern, you really should use the adjacency list, which is, again, another reason why in computer science we often use it. We're going to come back to how many entries are in the adjacency list, like I said, soon, but we don't actually have enough to analyze that fully yet. So put a little asterisk up there. I guess I could have written that, but we're asterisking in the air now, right? So if you want to see another representation, I included some down here of what's happening, including maybe some more specifics about how you might code this. These are two ways to represent the way you store the edges. The vertices are almost always only stored in an array or something similar to an array in practice.